right, let's get started. So, welcome to everyone here. I know it's late in the day already, so I'm sure people are already tired, and welcome as well to the people in the overflow room. I'm sure there's lots of people sitting comfortably there. My name is Stephen Kelly. I'm going to talk to you about how to refactor your code mechanically with Clang tooling. So just a little bit about me to get started. I've been around C++ and the open source community for C++ for about 10 years, 10 years. I did a lot in the KDE community. I then did a lot in Qt as well. And I did a lot in CMake, where I kind of created modern CMake over a few years. And more recently, I've been getting interested in Clang. And my interest in Clang has just been about tooling really so far. So I keep on hearing how Clang is great for creating tools, and I didn't know how to do that myself yet. So I said, well, I should learn to do that. So what I want to talk to you today is about clang-tidy. Clang-tidy is sort of the base tool on which we, create extensions in order to do custom refactoring of our own code. I'm going to talk to you about why you would refactor mechanically instead of manually, how to extend clang-tidy, what other tools can help you to write those extensions, and what problems you kind of might encounter when you try to do this kind of work. I'm not going to talk too much about the existing details of what's already built into clang-tidy. There's already a lot of resources about that on the internet. I'll just touch on that, and I'm not going to talk much about compilation databases either. They're sort of a requirement for you to create in order to do this kind of refactoring mechanically, but there's lots of resources about how to create those as well. For one thing, CMake will generate it for you. And what I want you to come away from this talk with is the idea that you can do large refactorings on your code. I kind of, maybe like a lot of you, tried doing text-based refactoring of my code years ago, and I thought it just doesn't work. But I want to show you that it is possible to do this kind of mechanical refactoring using today's tooling, and I want to show you that better tooling is coming in the future. So you probably didn't think that you were going to have to work today, but it's code review time. The question is, does this code pass code review? Does anyone think this code does not pass code review? Show of hands. A few people up in the front, okay. And of course, why not? No override. So we're using modern C++. This derived class needs an override specifier on its foo method. And the reason for that is if the base class has a slightly different signature, my foo in my derived class isn't actually going to override the foo in the base class. If I forget the const, for example, or if there's a different parameter in the parameter list. So what we want to do is have override there in the derived class, and then virtuals is redundant, so we can get rid of that. So this is sort of the end result that we want to go for. We want to remove the foo declaration, which is incorrect, and add a correct one with the override specifier. And we want to do that mechanically. This kind of thing, it would be very hard to do that in just a text-based refactoring tool. You need something which understands C++ in order to know that override is missing for one, and then where to put it and where to look for virtual and remove it. There's a lot of C++ knowledge needed in the tool for that. So that's exactly what clang-tidy does. It has, it's actually closer to 300 checks now built into it for doing atoms of changes like that. So modernize use override is the one which adds missing override to your classes. Modernize use null putter replaces uses of 0 in your code, which actually signify a null pointer, and replace it with the null putter keyword. So there's dozens of useful checks. There's a lot of library-specific checks in clang-tidy because clang-tidy doesn't have a plugin system. So you'll find checks in there which are specific to Boost or specific to Google's Abseil library and things like that. But it also means that if you're going to extend clang-tidy with your own tools, you're going to have to build Clang and clang-tidy yourself. So that's quite a disadvantage. So Godbolt actually has clang-tidy on it. So I can actually demonstrate that live for you. So here I have the same code from my slide with the problematic missing override. And I'm running clang-tidy with this modernize use override check. And what I get is this output telling me override should go here and virtual is extra, get rid of it. And you can run this on the command line, you'll get the same result. And if you pass -fix, and keep your eye on the left side panel here when I complete the word fix. So Clang has rewritten my code. It has then rerun clang-tidy and found no further issues. So I can actually just undo in the Godbolt window, and it does the whole thing again whenever Godbolt, expires its timeout. So that's the kind of thing we want to do with clang-tidy. But you're going to have your own code with your own types, your own functions, and everything that you want to refactor somehow. Maybe you have an old string type in your code base and you want to replace it with a new string type or a third-party string type, anything like that. And some of these kind of things, you might try to do them with just text parsing, and you might get some of the way there using that. So this one is quite simple. I think I'd be able to write a Python script which would replace old type with new type without too much trouble. Again, if we have a function returning a type and then we have a type inside the function and we return that, we have to change both places. So that's again not too difficult. I think I could do that with a Python script. Where it might get more difficult is if you have implicit conversions and other types. In a case like this where I'm returning a variable of type other type from a function which returns an old type, and I want to replace old type with new type, I might actually have to add new code in order to enable that conversion. Maybe that's not implicit in my new API. And this is kind of where you get away from what an IDE can do for you as well, because an IDE is, the IDEs that you use are starting to get refactoring tools in them too. They can rename functions, maybe some of them can rename types, but they're not going to know which code they have to insert in cases like this. But you might want to write your own code which is aware of that and can do this automatically. Just another case of the same thing. I'm now returning other type, and I need to do some conversion, in this case a static constructor, in order to make the code work with this new type. So again, there's just stuff that we need to insert, and it's not even as simple as the last time either, because now we have to insert code before and after the sum var in that return statement. So it's not just appending. So we want to be able to do large-scale refactoring. In cases where it's not possible to do with sed or a Python script, in cases that require semantic knowledge of C++ code, of your C++ code, in order to complete the refactoring. We want it to be automatable so that we're not doing it manually and spending a lot of human hours doing it. And we'd actually like it to be repeatable as well so that we can run it on our CI system. That means that we can, for example, fail a CI build if somebody introduces a derived class with no override. That could be useful. And we want it to be good enough that it doesn't break code. In practice, when doing these kind of refactoring tools, you tend to be able to get about 85 or 90% of the way there. After that, you hit into this long tail of special cases, and it's actually easier to just spend 1 or 2 hours fixing them up manually. Where that will occur, it tends to be something about templates usually, or something about macros. But like I said, you'll get 80 to 85 to 90% of the way there, and then just realize that diminishing returns. But the problem is, currently with clang-tidy, it's actually a little bit hard to extend. I myself I was never trained as a programmer. I actually did mechanical engineering in university. So when I left university, I thought a translation unit was a meter. Turned out that's very wrong. So I'm somewhere in there around professional level. And it takes a lot of knowledge about the internals of Clang today to actually create a refactoring tool like this. But we want to actually enable these kind of tools at every level of C++ ability. So the workflow of how you create a tool looks something like this today. You create a new check in the clang-tidy tool. You identify your C++ code to port. That's just literally deciding what you want to do. You create what we call a matcher query. I'm going to spend about half of the talk talking about that today, in order to match parts of the C++ code that you actually care about. And then you implement a fixit, which will do all of your replacements. So that will do things like insert the override keyword, remove virtual, replace one type with another type. That's essentially text replacement. But this is a cycle. So every time you create a tool, you run it on your code and you realize it's broken in some special case way. You'll fix your tool and iterate until you're satisfied, and then you're finished. So creating a new check is very easy. What you do is you go to the clang-tidy source directory, because you're going to build that anyway. And you need to run this script, add a new check. Checks are all categorized. So all of the directories here in this project are categories. So there's modernize ones. Those are the ones that tend to port your code to C++ 11. Performance, portability. When I create a new tool, I usually put it into miscellaneous. And the way you do that is add new check, misc for the category, and then make awesome. Because what this new check or porting tool is going to do is it's going to make your code awesome by renaming all of your functions. So this is default code that Clang creates for you whenever you run that script. Usually what you'll do is look at it, delete it, and then write your own stuff in there. But the places where you're going to write your own stuff are this register matchers function and this check function. So the register matchers function has a lot of calls to add matcher, and then what we call matchers. That's this function decal thing. I'll come back to that a lot later. All you should think about in this is that this is going to do something for every function declaration in your code. And the thing that it does is it calls check for each function declaration that it finds. And in this case, what this code is trying to do is, if a function doesn't already start with awesome underscore, we're going to add autumn underscore. So that's create insertion awesome. So we're going to come back to this a lot later, so don't worry too much about it now. But what you can't think about is that there's two important things. One thing is to create a matcher, and the other thing is to write the check function. So creating a matcher is what we're going to talk about now. This is basically the same code that we had in the text editor on the slide. And the matcher is there circled. we have function decl, bind, make awesome. That means that we're creating a binding for every function declaration in the code, and the binding is called make awesome. And then in the check method, we use that same name, make awesome, get it out of the results, and create insertion to insert our code that we want to insert. So that's just a basic two-step process every time. So yeah, now that we've created our new check, we need to identify the code that we want to port. And we're going to have some idea. It'll be replacing a type with another type, or renaming something, or putting classes into namespaces, or anything you can imagine. And you'll be able to match on anything that you can conceptualize in your C++ code. Your variables, your functions, your function calls, your classes and your instances of those classes, all of the types, etc. Anything with a name or anything with syntax, you'll be able to treat it as important and match on it. But it's always particular things that you want. In that case, I was looking for functions with a particular name. You might also be trying to match based on function return type, or by parameter types, or by parameter names, or by content of function or content of classes, such as members. So just a refresher, because I'm saying a few of these words multiple times. I'm pointing at the function declarations on this slide. Foo has two function declarations here. The second one is also a definition because it has a body. And bar is also a function declaration. And the call to foo, Clang calls that a function call expression. So that'll be represented as a call expression in how Clang models your code. So, you know, we've decided what C++ code we're trying to port. Next thing we need to do is write a matcher to match for exactly that source code. The way we do that is by writing an AST matcher. So we've already seen the function decl, that's an AST matcher. Here's another one, cxx method decl with is override inside of it. And that will match any method which is an override, whether it has the override keyword or not. So there's dozens of interesting matchers in Clang. You can match your functions, your variables, etc. And you can find them all online. We'll see later how you can discover them in a more easy way. And you can extend them with custom matchers. So what these things are doing is just calling APIs on the Clang AST classes, which Clang uses internally. So just a few more examples of AST matchers to give you an idea. To match functions which have the name foo, I would just write function decl and put hasName foo inside of that. This is what we call a predicate language, which means that anything inside of a matcher, if it's true, then it's added to the match set, and if it's false, we discard the entire function. So if we want to match on a parameter having a certain name, we can do that too with the hasParameter matcher. And then we check the name of that one. And we can check if a function decl is defined, if it has a body or not, if it's inline or not, etc. So anything that you can think of that relates to functions, you can write matchers to specify those. Just a few more. Parm-var decl is what used to match on parameters, if statements, call expressions, return statement. You can discover all of these matchers in the documentation. So just a few more examples now of what these would actually match in C++ code. So I have a function decl, and I'm saying inside of that, it has to have a certain name, myfunc, and it has to have a parameter whose name is input num. The 0 indicates that this is the 0th parameter, so that could be 1, 2, 3, etc. So this C++ code will match that matcher. this C++ code also, even though it takes a double instead of an int. However, these two won't match it. So the double input double will not match because it has the wrong name, and the yourfunc has the wrong function name. So those will not be part of the result set, and they won't be something that your second step will actually change in the code. But what I've done here is I'm looking at the hasName input num, and usually the name of a parameter is not what's interesting about it. Usually the type is more interesting. So how do you match on that? So what I'm going to do is replace hasName with hasType, and then specify the type as a string. So I'm saying if the type is a string, add it to the result set, otherwise discard it. And you can see the difference there. I'm not adding the functions which take a double to the result set. But that was just function declarations. If we want to match on certain call expressions, we need to use the call_exp AST matcher. And we map that to a function with the callee matcher. And this stuff, you might be thinking, how would I discover that? We'll get to that later. What you need to understand from this slide is just that if we need to port our function calls, which obviously you're going to have to do, you use the callee matcher to get to the function decal, and then you can do everything that we saw in the previous slides. You could check the return type of the function decal, or the parameters, etc. So in this case, I'm matching myfunc42, but I'm not matching notmyfunc42.2. Just another example. Here again, I'm looking at the parameter of the function, and I'm saying if that has the type int, then take it, otherwise discard it. And it's function calls, again, that I'm looking at, not function declarations, as a top-level matcher. So myfunc42, that's obviously going to match. myfunc42.0, will that match or not? I'm not sure. Myfunc A, will that match or not? Maybe, maybe not. It kind of depends on the type of A. And this is kind of why you have to do iterations when you're creating a clang-tidy tool. Because, sure, if myfunc only exists as one function, which takes an int, that will obviously match with myfunc42. However, if you have an overload, you won't match if you're actually calling it with a double. So you won't match the one which is expecting an int. You also won't match if it's a const reference or a non-const reference. So again, you can kind of see that these example function calls, you might first of all expect that they would match, but then realize they don't, and you'll iterate until you actually have something which matches all of the conditions you care about. Another thing you have to know about matchers is that you can bind results. So this is actually what you need to do when you're creating matchers in order that you can extract those results in step 2 and rewrite your source code. But you can also make multiple bindings in one long matcher expression. So here in the second example, I have a binding for remove param because I want to remove that parameter, and I have a binding for add awesome prefix for the function decal because I want to rename it. So I mentioned a few times that we have a discovery problem here. I'm showing you a lot of matchers on the slides. I said that they're kind of available in the documentation, but it kind of turns out that the documentation is difficult to parse. It's just a long list of matchers. You kind of have to click into each one, figure out what it is, and how you would use it. So what I've done is I extended Compiler Explorer. So this is just what you have on Godbolt, but it's running on my website, stevera.com. And instead of using it to look at assembly or compare the output of different compilers as you do on godbolt.org, you use it to query your source code with AST matchers. So in this case, I've written some query script here. So M is for match, but we can always use the M abbreviation. And down below that, we have output. So we're matching all function declarations. And you can see on the left side, we're highlighting each function as we go down. So because we're matching all of them, we get 3 results. But if I go up here and I write has name foo, I'm now only getting 1 result, and it's only the foo function. But you only know that because I showed it to you on a slide. What you actually want is for the tool to show you what you can use inside of function decal. And you do that by enabling matcher output from your AST matchers. And now for each result, it will show all of the matchers that you can copy and paste inside of that and still match this function. So it's saying that I can copy and paste hasName foo in there and I'll still match foo. And if I keep on scrolling down, I have awesome bar. And I can, it's kind of telling me stuff that I didn't know before. It's telling me that this is the way that I would match on return types. I would use returns as string void. What it's not showing is parameters, so let's add one. It's telling me that if I add has parameter 0 parmvar decal, I will be able to match on the parameter itself. And now I have an ID binding because now I have 2 bindings in my matcher expression. And it's showing me things that I can add which relate to the parameter itself. So I can use hasName in that as well. I can also use hasDefault argument because this one has a default argument, etc. So you can do a lot of discovery using this tool to find out where matchers are relevant. So that tool that I have running on that website is called clang-query. You also have it as part of your Clang build or your Clang installation. You can use it on your own source code locally because obviously you can't upload your source code to my website. And it works the same way. It has a script mode, which I'm using here, but it also has an interactive mode, which has code completion as well. That's, again, more helpful for you to do discovery. Okay, so I'm just again illustrating here that there's 2 steps in creating a clang-tidy check. The first one is to write your matchers. Here I've got 2 matchers in my C++ code now. And you can also see that I'm reusing a matcher twice. So here I have function decal and everything, and I'm assigning that to a C++ variable awesomefunc, and I'm binding it down here when I call add matcher, but I also use it again with the call expr matcher, which we saw before. So this is how you would add an awesome prefix to both your function declarations and your function calls. So once we've written our matcher and we're quite happy with it, we have to move on to the next step, which is rewriting our source code. And that's the bit that we saw before, where we use create insertion to insert an awesome prefix in our source code for all of the function decals and the function calls. And you'll notice that I'm creating in the insertion at get location of the function decal. It turns out that get location is the beginning of the function name in the declaration. All function decals have a begin location and an end location as well. And so you might think, okay, well, this is easy. If I want to change the type of a function, all I have to do is go to the begin location and replace whatever's there with my new type. But then, again, modernization in C++11 comes along, and you might have function declarations which look like this. And now you need to go to the end location of your function declaration and replace whatever text is there with your new type. And it turns out that instead of trying to do this at begin location or end location conditionally, you can use this big long string to get to the right location to insert whatever it is you want to do with the return type. So that's get type source info, get type lock, get as function type lock, get return lock. So that's the return location. How are you going to discover that? It's not very discoverable. But you have this problem with every class in the Clang AST. So function deco is only one of the classes in the Clang AST. Calls to member functions are represented with this cxx member call expr class. And it has a begin and an end lock as well, but then it also has a get expr lock. So you need to sort of discover that by reading the API today. So that's not so easy. And var variables in your C++ code are represented by the var decal. That again has a get location. It has a begin and an end location. But if it has an initializer, that's way at the end, just before the semicolon. So there could be a lot of other interesting locations in there that you care about. Maybe you want to insert or remove or replace something at any location that you can think of in that second line of code. Another thing that I want to move on or to point out before moving on from this slide is that the end location points to the 7. It doesn't point to the last 0. So the locations in the Clang AST always point to the beginning of the last token. So sometimes you have to advance your location to the end of a token. And there's a simple API for doing that. But it does trip you up sometimes. But we've come up against another discovery problem. How do we discover these source locations? They could be long strings. They could be just difficult to discover by browsing the API. So again, I'm using clang-query here. This time I'm matching on call expressions just to be different. And this time, instead of looking at matcher output, I'm looking at source lock output. And what that does is it prints out for each location in what it's matching, in this case the call expressions, where is that location in the source code. So if I want to get the beginning of this name, I can use get begin lock or get expr lock. If I want to get to the end, I use get end lock or get r per end lock, etc. And in the case of this second function call, there's more stuff going on. And it's showing me the locations there as well. It's not traversing down into the parameters themselves. I would actually need to use the other output, the matcher output, to discover that I need to use has parameter for that, and then look at the source locations of those matched nodes. So we can do that. So I don't know what's wrong with, oh, sorry. So now I'm matching the second argument to that function, and I get 7 plus 8, and I can see that there's a get expr lock and a get operator lock. They're representing the plus. And the reason I'm showing that is often you'll see that there's multiple locations which match the same place in your C++ code, but you want to use the one that's most semantically appropriate. So in this case, you'd probably be calling get operator lock to get the location of that plus if you wanted to, change it to a multiply. Okay, so that's how you discover source locations. And so for all of your create insertion calls or your create removal or create replacement, you can figure out what the first argument is going to be by using a tool like that. Okay, so that's basically it for creating a clang-tidy tool. You first write your matcher, and then you discover your source locations, and you rewrite your code, and that's it. But you can do that for one file or maybe for one piece of your code, and then you'll want to expand it out to your entire code base. And so then if you want to do that, you need to understand a little bit about what clang-tidy is doing. So if you just run clang-tidy yourself on a C++ file, it will process your header files and it'll change those as well. So if you pass -fix, you'll also get new rewrites of your files. So you'll end up with h file dash, because you're going to change that header file. If you then go to the second CPP file and try to process that one, it's including a header that's already been processed. And of course, that's not going to compile because you've already changed the header. So what you need to do instead is process your C++ files, but store the results as YAML files in what we call a replacement database. And process all of your C++ files one at a time, store all of the results in the database, and then at the end, extract all of the replacements from the database and apply them to all of your code at once. And then you need to do a rebuild and discover if you've made a mistake or not, and move on from there. So the way that you would run clang-tidy on multiple files is you would use the run clang-tidy script. That is something that is distributed with clang-tidy. There it is, run clang-tidy. But what that does is it runs clang-tidy in parallel using all of your cores, storing all of the results in the YAML database, and then afterward applying everything to your source code. So, what I just showed you in the slides is actually being done transparently for you by this run clang-tidy script. But once you try to do this on your code, you're going to run into a few issues immediately. One of them is that you'll need to have all of your generated files pre-generated. So, for example, if you're using Qt and mock, and if you're including your mock files in your C++ files, which you might be doing, you'll need to actually do a full build first in order to have all of those mock files generated. Otherwise, your stuff just won't build. So anything else being generated as well in your build system will have to be already present because, when you're running clang-tidy, all of your custom stuff is not being run. Another issue that will come up is time. It takes a lot of time to run clang-tidy on all of your source code. It takes about as much time as compiling your source code because that's essentially what it's doing. But you can speed it up if you use Unity builds. You can speed it up by using pre-compiled headers, and you can speed it up by using some tricks that you have from build distribution. So it is possible to use build distribution tools such as Ice Cream to have clang-tidy be run across your whole network instead of serially or almost serially on your computer. And really all you need to do is rename the clang-tidy executable to clang++ and have it output .obj files which actually contain YAML. And that's generally enough for those kind of tools to send it back to the host computer. So that's almost everything that I have to say about tooling. I did say in the description of this talk that it's about the current and future Clang tools. So I want to show a application that I've been working on over the last few months. I mentioned that I have a long background with Qt, which is of course a Norwegian product here. Trolltech started it a long time ago. So what I've done is just a small application which we can use to run clang-query in this case. And what I have is multiple AST matchers. and I can click each one to get results. And I get annotations in my C++ code as well, so that all of the feedback is very immediate about whether my matcher is working correctly or not. So in this case, I'll say that I want to match function decals unless they're implicit. And I get my annotations here. Root is the default name of any matcher that you make. We can turn off binding of root and add our own binding. And we get that as our annotation. And that's relevant if you're also binding parameters or something. You'll get annotations for the parameters as well with different names. We can also click around here on the right side and view which source code is being referred to there with each match. So this is kind of a step up in usability from reading the text output of clang-query. You're getting everything immediately to you, and you're able to see in your source code how your matcher is working, if it's doing what you want. So just looking at this other matcher, it's reusing a matcher that we might want to reuse. So you can use this let inside of clang-query script in order to reuse fragments of AST matchers. So I'm doing that here. I'm saying function decals which match multifunc, which is something that checks the name of the function, and parameter count is 1. So I'm running that. I better bind root again. I'm running that, and it's showing me that there's only one match, and it's this place in the source code. Nice and easy. But when you're writing matchers, you'll often have typos. You'll be looking at your C++ code saying, I think that should match, and you'll be looking at your matcher saying, I think that's a correct matcher, but not getting the results that you want. So what you can do then is hit debug and click whatever line that you think should be matching. And then you get what I call stethoscopes. You get a little circle for each Clang AST node that it knows about. So we get one for the function itself, and we get one for this parameter. So if I click on the one for the function, I get this red annotation that has name is actually not returning true. So then I realize my mistake, multiply 42, I rename that, and it all goes green. And again, if I have the wrong number of parameters that I'm expecting, it shows you exactly why that line of code is not matching as you might expect. So if I try that for the second stethoscope, it's failing to match at the first level because parameters are not represented by function decals, but by parm-var decals. So that's something that doesn't work. That is deliberately not working. We can also see locations. So where am I? Yeah. So I'm it's getting a bit noisy. So I can also see locations using this stethoscopes tool. So I'm again matching multiply 42 only. And you can see all of the different places where it's determined there's a location that's interesting to look at. So if I click in the stethoscope, it gets highlighted on the right as well, if it works. And this is basically the source code that you would just paste into your clang-tidy tool using copy location. And you would be able to replace anything that you like by visual inspection and discovery of the source code just by looking at it and examining it with the stethoscope. So maybe just a bit more of a concrete example of that. What I have here is a matcher which matches any variable declaration which is const qualified. And there's a few other things there about L-value references, and I want to not match parameter parm-var decals. So let's just copy that into clang-query to see what it matches. And so it's creating a binding called port const, and you can see in the source code where that represents. So there's one here inside of some header.h, const adder, and there's this one, const multiplier. The problem, of course, is that this code is not const correct. The const is clearly on the incorrect side. That is why this project is called const cartography. It's using west const instead of the correct east const. So what we want to do is write a tool to fix the source code to make it const correct. So we have our matcher that's matching any const variables in our code. And down here we have some JavaScript. Screen resolution is hitting me, I think. Port const is assigned to a variable from the port const binding. That's similar to what we saw in the slides. And we're going to remove from get begin location to something which we need to discover using this tool. And we create a removal for that range. So we need to find out what we need to use as removal end. So we go back to the query, we show locations to see our stethoscopes, and we realize that we need to match up to this location. So that's what it's telling us. But there are two results for the exact same column. And semantically, I think this one is more correct. So get type spec start location. So copy location there and say that we want to get it from the port const JavaScript variable. Oh. And the output of that is already shown on the screen. So const is gone from this version of multiply. And we can see a diff as well to make that a little bit more clear. Okay, that's half of the job done. Now we need to insert const on the correct side. So we just copy and paste that. And we say create insertion. Then at the insertion point, which we don't know yet, and what we're going to insert is const. So var insertion point equals what? So back to clang-query again, so we can see locations. And where do we want to insert it? Let's say just before mult, just before that name. So I click on that, and it's telling me to use get location for that. So copy that back into my JavaScript and port const dot get location. And what do I get now? I'm actually going to start with the output. You can see that I've made a mistake. That was actually deliberate. I'm inserting const instead of const. And what this tool has done is that it has made that replacement and recompiled my code. And I'm getting Clang diagnostics now telling me this actually doesn't compile after you've run your tool. So Clang has a very clever internal virtual file system. So all it's doing is rewriting modified files in memory, which could be headers, but not writing anything to disk, and redoing a compile with that. So if I fix up my tool and insert the required T, recompile diagnostics window goes empty, and the output is showing me that I have inserted const in the correct place. So that's cool. So I've processed one translation unit and made it const correct. But of course, that's not enough. We need to be able to run a tool like this on all of our code at once. So that's what this bulk porting dialog is for. It's just using the exact same query and the exact same JavaScript that I already showed you. And we can filter on file names here as well, because often you will want to run your tool on particular parts of your source code, particular directories or files matching certain names. So you can just match whatever files that you want there and hit run, and it'll actually run the tool on all of your selected files in parallel once again, and give you the output and the diffs for everything here as well. So you get a green line or a green box for every successful recompile, and a red box for unsuccessful recompile. So if I click into other file here in the results, you can see in the diff that I've actually generated incorrect C++. I've put the const after the ampersand. It needs to go before. So this is where we would iterate, fix up our code, and we would do that all in this tool without recompiling clang-tidy until we actually have a working tool. And then you would probably have to rewrite that in C++. But you would only have to rewrite that in C++ if you want to repeatedly run this code. What I have here already is writing the const correct code, and I can write out all of the files there with this button. And that has changed my code, so I can verify that in the Git repo. So success aside from this part. And like I said, with stuff like that, you would either decide to fix it up manually or fix up your tool. It's really up to you depending on how much it's worth it. Okay, so just one last thing about this. When I was blogging about creating clang-tidy tools, I was blogging on the Microsoft platform because I was working at Microsoft at the time. And one of the comments that I got on the blog was that Clang sounds like a Klingon general. And when I started writing this tool, I thought, well, I want success, in my refactoring efforts. And so I thought, well, Klingon generals and Klingons and success, what'll I call it? Of course, it's Kapla. So hopefully that'll become available to everyone in the next few months. So just a few slides about how to, things you might encounter when trying to create your own tools. You should focus on expressions. You have a lot more expressions in your code, and they tend to vary a lot more. So when you're running your automated tool, focus on where the expressions are different and try to capture as much of that as you can. Get familiar with all of the Clang AST classes. There are a lot of them. The API documentation is online, so typically if you Google one of them, you get the right result. And they have diagrams and everything. So you can port expressions in that way. Porting types is generally easy because you just specify a string for whatever type it is that you care about. So just again, to emphasize a point here about AST types and AST matchers. The call expressions in this source code, there's only one, bar. And the function decals, there are 3. And if we're writing AST matchers, the way we get from the call expressions to the function decal is by using call-e. But unfortunately, it's not so consistent. So if I'm interested in the expressions which reference declarations, which typically you would use for variables, here are all of those. So they're referencing existing variables. Said variables are circled here. And if you're interested in some attribute of a variable when you have a decal ref expr, what you use is the to caller. So, you might be interested in variables, so this expression, and then say, I only care about it if it's a use of a variable called I, whatever. So unfortunately, there's this kind of inconsistency in those matchers, and you'll just kind of have to get used to those for now. Perhaps we can fix those. I'd like to make them all just 2, so that 2 is always the right thing to write. So here again is the workflow diagram, basically, of how to create a clang-tidy tool. With the GUI that I showed you, hopefully it just gets a bit smaller. Sorry, somebody's trying to photograph that. With the GUI that I showed you, hopefully you'll do the same thing, but with quicker iterations. You won't have to recompile clang-tidy all the time. You won't have to write C++ code. So you'll just really do the same thing without all of the slowness. So yeah, I hope I've shown you that large refactorings are possible in your code for your bespoke needs, which nobody has thought about before. And the tooling for that, there's already good tooling available. There's better tooling hopefully coming down the line. So you don't have to be sort of afraid of doing this kind of stuff in your code. So clang-tidy is used to do that. Clang-query is used to discover it. You can use the reference for all of the matchers and for all of the Clang classes. And you can distribute your workload in order to actually make it faster to run using a build distribution system like Ice Cream. That's all I have. If you're interested, there's time for questions. You can see my blog. You can use my Compiler Explorer website. And you can use Stack Overflow to use these things as well. So I'm looking at the Clang AST matchers tag, and I'm always interested in pointing out to people how to discover answers to those questions. So I'll just let people parse that to decide what to do next. So are there any questions? The question is, why JavaScript? The reason is Qt has bindings for JavaScript. So Qt has a JavaScript engine, and it was easy for me to create bindings to the Clang AST, which would work with the Qt JavaScript engine. So that's why JavaScript. I could do it with Python as well, because PyQt exists, but I haven't done that yet. Do you have a suggestion of another language which might be useful? C++. Well, you can't interpret that easily. Anything else? Okay. Well, thank you for coming. I hope you enjoyed today and the rest of the conference.